Have you ever wondered how to measure the speed of light? I mean, I've never measured the speed of light, but I'd love to do it somehow. But how could you measure how fast light is travelling? I mean, it's everywhere around us and we can't even see it or weigh it. Oh, of course!
Yeah.
Cheese!
Yeah.
We can measure the speed of light with cheese!
I can help you, yes!
Thank you, cheese man! Let's do it!
Yeah.
Woo! Yes, we can prove the speed of light using just some cheese and
Yes,
a
cheese. microwave.
Cheese and a microwave. So, cheese man, could I have
Cheese.
some cheese, please?
Cheese.
Cheese, yes.
Cheese. Cheese. Cheese.
Thank you.
Cheese.
Thank you.
Cheese.
More, we need more.
Cheese.
Yeah, we need more.
Cheese.
Keep it coming, keep it coming.
Cheese.
Yes, lovely.
Cheese.
Yes, lovely, great. Thank you, cheese man. Thank you. That's enough cheese.
No problem.
Thank you. Thanks very much for your help. So now we have our cheese. We're going to be able to use this cheese to figure out the speed of light by putting it inside our microwave in a certain orientation. So we need to take our slices of cheese, we unwrap them from the packaging, and we just put them down on some sort of a flat surface. A chopping board made of plastic or wood is fine. Just don't use anything metal because it can't go in the microwave. So lay them out just nice and neatly like that in a nice flat pattern. Now you're probably wondering what is going on at this stage. We've sliced up our cheese nicely in a nice flat pattern here and we have a microwave oven. What has this got to do with measuring the speed of light? Well, what does a microwave do? It heats up food, but how does it do it? It uses a thing called microwave radiation. No, it's okay. It's not so scary. It's not harmful. And it's just a name that we use for a particular type of a wave. So microwaves, are microwave radiation. It's one and the same. The important thing is that it creates waves that have a wavelength and also a frequency. Now, we've also said in previous episodes that light is a wave. Light is a wave that has a wavelength and a frequency, just like microwaves. In fact, microwaves and light waves are exactly the same thing, they're just waves of different lengths. So that means the microwave oven uses a special type of light that we can't see to cook the food. And if we can somehow figure out how long those microwaves are, we'll be able to be closer to figuring out the speed of light. And that's where the cheese comes into it. We've loaded this bad boy up with her cheesy cargo and we're ready to get started. Now, what are we expecting to see here? Well, inside a microwave, these microwaves, they're generated here and they resonate. Now, if you remember our episode that we did about wind instruments, we talked about sound waves resonating inside an instrument. It's the same principle here, and you'll see similar patterns here too. You're going to see these places where these waves go up and down and places where they kind of stay still. And how the microwave actually heats the food is it jiggles the water molecules up and down and up and down. So at the places where those microwaves go up, down, we're going to see more cheese melting than in the other places. And from that, we'll be able to figure out how big the waves are. Now, the important thing to do before you do this is to take out the rotating plate at the bottom of the microwave, because that's going to spread that heat the whole way around, and we don't want that to happen. So let's take a look. Let's turn on our microwave. Let's see what kind of patterns we see in our cheese, and let's see if we can figure out how long the waves are of our microwaves. So those microwaves are bouncing around inside here, but they should be setting up in a resonating pattern. So that means certain sections of the microwave, will have more vibrations of those waves, those pointers that go up and down, and other sections won't. That's why they spin the food around in the microwave so it gets evenly heated. But we don't want that. We want it to be still so we can see where is the most microwave radiation and where is the least. Aha, see the bubbles starting to arrive. So that's where there's more heat than the other locations. See those spots? Right there, it's very clear, isn't it? We can see that there's more heat in those locations and less heat in the other locations. That must be where our waves are interacting. Okay, we have something. Let's take a look. The first time we did our experiment, we saw this weird pattern appearing in our cheese. Some parts of it are super melted and other parts are completely unmelted. So this means that our microwaves are giving more energy to these melty parts and less energy to the non-melty parts. Now what we're looking for here is we're looking for some type of a pattern, yeah? Some type of repeatable do, 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 do. Because that will lead us to think that there's a certain wavelength of wave going through here and we can figure it out. But this first one is too messy. We can't figure out any sort of a pattern. So we tried again. We moved our cheeses, instead of being on the bottom of the microwave, we moved them up to the middle. Because this is a three-dimensional space and it's quite complicated how the waves move around. But this time we actually saw quite a nice pattern. See this here? We have boom, 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 boom. We got these 4 different locations, one after the other, and they kind of repeated up here as well, where we actually saw the cheese melting. So that leads us to think that this could give us an idea of our wavelength, okay, based on the distances between these melty parts. Because remember, whenever we set up those waves inside some sort of a box that are resonating, there's a particular pattern that they get. And we can calculate the wavelength from that pattern. So I measured my wavelength using my trusty measuring tape. And the average value I got from measuring these out was 16 centimeters. 16 centimeters. But what's this got to do with figuring out the speed of light? We just know the wavelength of our microwaves inside here. Well, there's a special equation in physics that tells you if you know the wavelength of a wave and you know its frequency, you can calculate the speed. So we've got the wavelength, how do we get the frequency? Well, if you look on the back of your microwave, you'll see a little plate, and written there should be the frequency. On ours, the frequency is 2,450 megahertz. What does that mean? That means 2,450 million waves pass through every second. So we drop our frequency and our wavelength into this special equation, multiply them by each other, and the answer we get is the speed of light. So what did we get for our answer? We got 392 million meters per second. Think about how fast that is. 392 million meters in every second is how fast light travels. So the accepted answer is 300 million meters per second. So we were a little bit off, but I think for experimenting with a few pieces of cheese in a little microwave, we didn't do too bad. Okay, we did it. We figured out the speed of light and we couldn't have done it without our cheese man. So thanks so much for tuning in, guys. Thanks so much to the cheese man, and we're looking forward to seeing you on the next one.
See ya. That's not so fast.